Imagine you've been walking the circular perimeter of a sprawling park. You're exhausted, checking your smartwatch to see how much farther you have to go. You eventually complete one full lap and arrive exactly where you started. At this point, we have to ask, kitna distance, or displacement? Physically, the journey was significant. You've burned calories, and your watch shows a distance of 2 kilometers. But mathematically, your net movement is 0. Because you ended up exactly where you began, you haven't been displaced from your origin. To understand physics, we have to separate the physical experience of the effort from the geometry of our final position. This distinction starts with distance. Distance is a scalar quantity, a simple number that measures the entirety of your journey. It depends strictly on every turn you take and is always a positive value. Notice how this line accumulates length. It counts every detour, every backtrack, and every obstacle you navigate. Distance only grows, it never resets. Displacement is different. It is a vector quantity that ignores the details of the journey and focuses only on the shortest possible gap between your start and end points. This glowing arrow represents displacement. Because it's a vector, it requires both a magnitude, the straight line length, and a specific direction to tell the whole story. While distance accounts for the physical path you traveled, displacement records where you ended up relative to where you started. On a one-dimensional coordinate line, direction becomes even more specific. This leads to a common question. Kya displacement negative ho sakta hai? Imagine taking a few steps forward, stopping, and then walking backward until you pass your original starting spot. On this number line, your distance scalar just keeps increasing as you walk, but your displacement vector reverses direction, crossing 0 and pointing into the negative zone. In vector math, a negative sign isn't a value less than 0. It's a directional instruction telling us you moved backward relative to your starting point. This brings us to a specific case. Kab distance or displacement barabar hote hain. They only match under one condition. You have to travel in a perfectly straight line, moving in one direction without ever turning or backtracking. But what about a curved path? Circular motion made displacement ka. Think about walking halfway around a circular track. Here, the distance is the curved arc length, but the displacement magnitude is just the straight diameter connecting the two sides, calculated simply as 2 times the radius. This demonstrates a consistent geometric constraint. The actual path taken will always be greater than or equal to the straight line displacement. Let's go back to the beginning, completing that full circular lap in the park. Since your initial and final coordinates are now identical, the straight line distance between them has shrunk to 0. Mathematically, you haven't changed your position at all. If your displacement can be 0 while your distance is in the thousands, why does physics require us to track both? Because these two measurements are the inputs for different rates of motion. We divide distance by time to find average speed, the pace of your effort. We divide displacement by time to find average velocity, the rate of your net change in position. Speed tells us how fast you moved along the path, while velocity tells us how quickly you actually displaced from point A to point B. Understanding the difference lets us look at the same movement and see 2 different datasets. Distance tells the journey, displacement tells the result. No matter how